resource from QuestAPlus. It's the released items of 2013, and it's an old diploma from November 2012. So we'll go through this. It really does cover everything you need to know, so this is a good way to test if you're ready for the diplomas coming up. And the first part, just to mention, is the percentages you're going to see at the side as we go through it is just telling you how well it tested, how many of the students got it right. So this first one is talking about methane gas burning in a fireplace, and then asking what type of reaction occurs. So if methane is burning, it's going to release heat. So it's going to be an exothermic reaction. And then it's asking about the original source of energy. And we want to know that the original source is always going to be the sun. So even though you might be tempted to pick something else, original, always the sun. The next one is showing that we understand enthalpy, whether it's written within the equation or as delta H notation. So the first thing we want to do before we even get to the question is rewrite in delta H notation. So if it's on the reactant side, make your delta H positive. If it's on the product side, make it negative. Now it is asking to number our equations based on the reaction that absorbs the most, so the most positive, to what will release the most, so the most negative. And it is asking per mole of carbon dioxide. So if your equation doesn't have 1 mole, we have to divide the enthalpy to reflect that. So the first two equations have just 1 mole, so we're fine. The third equation we'll have to divide by 2, and that will give us negative 257.05 kilojoules per mole. And then the last one we'll have to divide by 3, just so we're showing again per 1 mole of what's the carbon dioxide. So this is positive 124.7 kilojoules per mole. Then you can order it to most positive, being most absorbed, then the next positive, then to most negative, being what will release the most. Moving on, we're starting to look at Hess's law short. So we have the enthalpy of a reaction. I already went in and filled in these values, which you do get from page 4 or 5 of your data booklet. That remind you of a couple things, that if you have a coefficient in front of your compound, make sure to multiply, because the values you see on your data booklet are kilojoules per mole, and that any element that's alone is going to have an enthalpy of 0. Now, in really short notation, I just write the delta H of the reaction is products minus reactants. So you would get the sum of your products, which is that negative 393.5, and then you'd want to subtract your reactants. So adding your reactants together, and you'll see that the answer is going to be positive 164.7. And then asking the enthalpy change per mole of hydrogen. Well, within the equation, you have 4 moles of hydrogen. So you'll just take that value and divide by 4. And when you do that, you'll see your answer is B. Our next one is starting to look at just the equation. It actually looks like it's going to be more complicated. But if it asks you about equation 1, and the enthalpy is given, then talking about the energy of the products compared to the reactants. So it says the reactants either have more or less energy than the products. Because it's negative, we know it's exothermic, and if you just did a quick potential energy diagram, we'd see that drop in energy, and reactants then are higher, so they have more potential energy than the products. So just that first part, and then it's talking about if your energy, so this value here, was included in the equation, because it's negative, you will see it on the product side. So this one seems like it's getting a little bit harder for 55% of students to get it correct, but hopefully you're not overthinking it and you know what it's asking. Question number 4 is showing potential energy diagrams, but it's not telling you the delta H. So same thing, I just went ahead and filled in some values. This one's very messy, but this is negative 296.8. And you're doing the same thing as before. You're taking your delta H to find the reactions enthalpy, products minus reactants. When you do that, you'll figure out that your enthalpy is going to be negative 1039.6 kilojoules. So because it is negative, we are looking for that drop. So you can take away C and D. And then you just want to make sure that your reaction values, like the values we're seeing here in the reaction with what we see up here, are matching. So if we manipulated this equation in any way, we'd also have to manipulate your delta H. right? So like in B, it looks like we're dividing everything by 2. If that was true, all these coefficients also have to be divided by 2. So this one, the one that matches, is A. Okay, this next one, oopsie, sorry about that. This next one is showing that you understand calorimetry. So it gives us some information. You are mixing an acid and a base together, and it does tell you the final mass, which is nice because sometimes it doesn't, and you have to remember if you're mixing an acid and a base, then you add your volumes so that it will be like water. Then it's asking about the energy transferred. So I set this up like a calorimetry question, but we really just need that energy. Whatever we get here, the Q value, that even though it says NH, it's not asking for a specific substance within the calorimeter. It's just asking about the overall energy. So we can just fill in what we know. We know it's 100 grams. We know the specific capacity of water. The other part here is just remember your assumptions if needed. And then the last part is looking at that chart, taking your highest value, subtract your lowest value, and plug it into your calculator. You will see the value is going to be a bigger number, 4,609. And now because it's energy based on the units within, it would be in joules. Your answer here needs to be in kilojoules. So just divide by 1,000 and you would get 4.61 kilojoules. So hopefully you find that nice and easy. Now this second part is a continuation question. Because our temperature here is when we do your final minus initial, or even when you see that your temperature is getting higher, right? That is showing that you have an exothermic reaction. Also, this would be negative. So if it's exothermic, right, for question number 5, we can write out, we can write out what we see, and we just want the graphs to match. So this is endo, and now we have our two exothermics, and now just noticing that if your reaction is exothermic, your delta H has to be negative, not positive. So your answer here is C, and I think that's maybe why this was tested a little bit lower than some of the other ones. The other part in a lot of your diploma level science courses is to be able to answer questions about experiments, knowing what's manipulated, responding, and controlled. So in this one, it's just reading over, you were asked to design a calorimetry experiment to compare enthalpies of kilojoules per mole when burning samples of equal mass of methanol and ethanol. So we're changing the fuel. So because we're changing the fuel being tested, that is what's being manipulated, right? The manipulated is the thing you change. Controlled, what can we keep the same? We can keep the same the calorimeter we use, we can keep the same room temperature, we can keep a lot of things the same, so whatever we can keep the same. And then responding is the thing you measure. So when we're going through this, reading manipulated variable is the type of fuel. Well, we do know that, so it's one of these. Controlled is not the type of fuel or the mass, but going up here, and the controlled variable is the temperature change. That's going to be what's responding, and the only one that matches here is B. So I like that this tested well, because I find in our classes that we kind of slack on knowing the controlled, manipulated, and responding, which should be nice and easy questions for us to get. This next one, we have some information. We have the reaction. We can get the delta H from the reaction, and it's asking when we produce if 2.50 grams was produced, then the energy transferred is. So when you're looking at this formula, again, I know it gets confusing, but we want to remember that this H within the formula comes from the reaction. So even though you could write this as delta H is negative 1648.4 kilojoules, it's from the reaction. So this H is the delta H of the reaction. This delta H is energy released or absorbed to the environment. So because it's asking about Fe2O3, you start with the mass, use the mole ratio, that's molar mass, to get to moles, and then multiply by that enthalpy. Remembering though, because it's asking about the Fe2O3, because it's a molar enthalpy, you'll have to divide by the amount of moles. And once you do that, you'll see that your answer, sorry, I just have to double check because I have it written down, was going to be negative 12.9 kilojoules. And then I get that question quite often. What do you do with the negative? Well, the negative is going to be implied. If the energy is being transferred, we know that 12.9 joules would be transferred. So moving on for this one, and again, this one's a little low, and I think the biggest thing missed here is putting the enthalpy in the wrong place or forgetting to divide by 2. Okay, so this next one, we have to get a bit of information from the graphs. So it's asking about the energy transfer during the process. So we want the delta H of the overall reaction. So we're going to see from equation 1 what the delta H will be by just taking the difference here, and you'll see that you have negative 200.8. And then from equation 2, same thing, calculate your delta H is negative 191.1. Now with this, luckily, you don't need to flip anything, and we don't need to multiply or divide. So you're just going to add these two together, because just by adding them together, you'll see your NO2 canceling, your NOs canceling, and we're left with what we need. We have 1 O3, 1 oxygen, and on the product side, you have 1 plus 1 gives you your 2 oxygen. So we have that, we're adding it together, and you'll see your answer is D. Now, another part it's asking in equation 1, which I just rewrote down here, nitrogen monoxide, so this here undergoes blank, and the nitrogen atom is either going to gain or lose electrons. So if you look at nitrogen, it is changing from positive 2 to positive 4. That means you are losing electrons. So if you write down oxidation involves loss, we know it's oxidation, and if you're losing electrons because you're becoming more positive, this one, the answer would be D. Okay, so moving on to question number 9. I know that in my class we have used this question before, and it usually, again, stumps people, so just be careful for what it's asking. So it's asking for the molar enthalpy of formation of solid sodium azide, which we see is up here. Now, when you do look at equation 1, when we're looking at this reaction, we want to see that the sodium azide is decomposing. So if we write this in, delta H of our reaction is going to be the opposite of formation. So this is going to be negative 21.7. And then asking for the enthalpy of the reaction, the other part, is that this is per mole. Our equation is representing 2 moles being decomposed, so we need to multiply this by 2. So flip the sign, multiply it by 2, and you'll see your answer is A. The next one is just assigning, it's asking for the metals. So assigning your oxidation numbers, figuring out what the metal equals, and we'll see that this is 1003. And if you did need more help with that, let me know, but this one tested pretty good. Okay, I love that this one tested good as well, because building tables can be a little bit challenging. So what we're looking at is these 4 reactions. We want to remember that if we see products, that it's spontaneous. So when you look at your reaction and you identify your OA and your RA, so looking here, we see we're going from positive 4 to positive 3, meaning you gained an electron, so that's reduction, so that makes this one an OA, and then the PD, if we take a look at that, it's going to be an RA. So when you go to place it on the table you're creating, because you want it to look like page 7 of your data booklet, and I usually just leave out the electrons within, just because we just need the placement of the OA and RA. We want to place the OA higher than the RA, because it's a spontaneous reaction. The same thing would be in the second one. The OA needs to be higher than the RA. The third and fourth help us figure out the order of the last 2, and because there's no reaction, we want the RA to be higher than the OA. So once we've made our table, then you read your table. Strongest oxidizing agent is just like you see in your booklet. Top left, as you go down, it gets weaker. If it asks you about the strongest reducing agent, bottom right, as you go up, it gets weaker. So in this case, our answer was B. Okay, now question number 11. I do not enjoy these questions because they're long. I just gave an example with the first one. If you have an oxidation reduction reaction, that means you have something that's undergoing reduction and another reactant that's undergoing oxidation. So you can identify an OA and an RA. If you can't find an OA and an RA, it's still a reaction, it's just not a redox reaction. So I looked at the first one, I identified my oxidation numbers. I saw that I have copper as my OA and this acid here as my RA. because I have an OA and an RA, we have a redox reaction. If you move on to the next one and you assigned your oxidation numbers, you would see that there's no change in oxidation numbers. So this is not a redox reaction. So you go through all of them, keep doing, assign those numbers, check it out, and you'll see that only reaction 1 and 5 have an OA and an RA. So those are the only two that are redox reactions. Now, again, it's not that this is hard, it's just long, and you have to just assign those numbers and look for the change. Okay, so question of the numerical response, number 5. This one's asking the species that can oxidize chromium 2 positive. So what I just wanted to take a look at, if you're being oxidized, you are a reducing agent. Why that matters in this question is chromium 2 positive does appear as an OA and an RA if you look at page 7 in your data booklet. So we want to look at it as an RA. Now, if you're able to oxidize the RA, that means you're spontaneous. So you need an OA on the table above it. So anything above the chromium 2 positive as an OA can oxidize. So just going through placement, it would be F2, so fluorine gas would work, AgI would work, number 6, the nickel ion will work, and number 7. So just be careful with this one, take your time, look for placement, but I think overall it's not a bad question, it's just understanding this part. This next one, being able to identify the reducing agent and the substance being oxidized. So you are going to assign your oxidation numbers. And I also just want to remember when they're asking questions like this, remember to always pick a reactant. So even if they have products as an option, you know not to pick it. I know in this case we don't, but if they do, don't pick it because products just help us see what's happening, but the reactants are what's reacting. So that's our OA and our RA. So once we assign our oxidation numbers, we'll see that H2S is our reducing agent and the substance being oxidized is also the reducing agent. So the answer here is A. Okay, so moving on, we have some information about the separation of potassium, molten potassium hydroxide. Because it is a separation of 2 ions, or that metal being made into 2 ions as a liquid, we do need some inert electrons in here. Now, this part though, from the question saying electrolysis, we know that it's going to be non-spontaneous. If it's non-spontaneous, the cell potential has to be negative. And again, these two just kind of go hand in hand, negative, non-spontaneous, positive, spontaneous. Now, asking about the reaction that's happening at the cathode. Cathode is reduction, and reduction means you're gaining electrons. So you can rule out the last two. We also can rule out B because there is no water present because we are molten. So that's the state is pure liquid. So the only possible answer here is A. Moving on to this one down here. So I did find this one a little bit confusing to start. I like that more than half of the students got it right, but just going through it, it's asking first for the overall reaction. So we can tell what's happening, right? Because we have electrons going from the anode to the cathode. And we can look at our reaction and see these two half reactions and know if we want the overall reactions, we have to add them together, but to add them together, we have to balance electrons. So the lowest common denominator, multiple, between 6 and 4 would be 12. So you will want to multiply that first reaction by 2 and that second reaction by 3. So if this one is all multiplied by 2 and this one is multiplied by 3, we have some coefficients in here, 2, then we'll have a 2, this would become 12, and, 6 times 2, 12, and the last one also becomes 12. If we're multiplying by 3, we have 3, 12, 12, and 4. Then what you can see is some things will cancel out, like your electrons will cancel, your hydrogens will cancel, and the other part that will cancel is 2 of the waters on the reactant side will cancel with 2 out of the 4 on the product side. So this will go away and this will reduce back to 2. So I know this looks really messy, but hopefully you can see now our coefficients are going to be 3, 4, oh wait, water, 3 times 2. Oh, this was a 6, not a 4. That's why when we take away 2, it's going to be 4. Good thing I have my answer key here. And then 2 and 2. Okay, so the other part, when we're going into the second one, we're going to get a little bit of information. They'll tell us that this reaction over here is going to be positive, 0.80, and this part here, so we're getting that just from the question. And then this second half reaction you get from your data booklet is positive 1.23. Now, if you missed this about the electron flow and you haven't identified your anode and cathode, you can always identify it as your cathode has a higher cell potential. So when we come down to calculating the cell potential of the whole cell, your cell potential is going to be your cathode subtract your anode. So your cathode value subtract your anode value, and you will get 0.43. So I'm not sure why that tested so little. I think maybe just getting that anode and cathode confused. Moving on to question 71. Sorry, 71% of people got it right. Question number 8. I did actually find this one a little bit confusing because it's giving you information about chlorine, but then asking about the mass produced of magnesium. And usually when it's kind of like a cell stoichiometry question, they don't ask you to use the equations. You're looking for half reactions. But in this case, because this is a 1-to-1 ratio, if 0.893 moles of chlorine were produced, then we'd also have 0.893 moles of magnesium produced. So if we know that, then we can simply just use molar mass of magnesium and see that your moles cancel and we're left with grams, and that's what it's asking for. So cancels and grams becomes 21.7. Okay, so keep going here. The next one we have a titration. In this case, one of the things we want to recognize if we do have this titration or redox titration, we had 4 trials. If you take a look at your trials, you'll see that trial 2 is off, so don't include that in your calculation. Remember, we add and subtract 0.2 to see which ones we're going to keep. So all the others are close enough. We'll keep all the others. Calculate your average value by adding them up and dividing by the amount you keep, so 3. Now, what we're using here, this part is telling you it's the volume of I2. So what we can start with is getting to moles of I2 using the volume in liters and concentration. So that part, concentration, was given to you. We'll see that liters cancel, and then you're at moles of I2. Now it is asking you about the concentration of vitamin C, which is this part here. And it is a 1-to-1 ratio. So once you get moles of I2, if you do multiply by your molar ratio, it's just changing your moles from iodine to the vitamin C. And then lastly, you're going to divide by how much you are doing each time, which you're measuring out 10 mils that you're titrating with. So you'll plug that all into your calculator and you'll see here your answer is C. Okay, so this next one is still looking about the titration, and this is more of a theory question that tells us we understand titration, and it didn't test the best. It got 37% of students got this right. So the first one, it says the indicator change colors at the end point. That is true. Endpoint lets us see the color change. If it did say equivalence point, you would not include it, because if we cannot see the equivalence point, we can only see the endpoint. The grapefruit juice should be placed in the burette. That is not true. It should be in the Erlenmeyer flask, because that is what we're going to react with, and we are figuring out how much of the I2 we need. The next one, the sample should be measured by a pipette. If you're measuring out 10 mils, a pipette is going to make you the most accurate, not the graduated cylinder. And then question 6, iodine undergoes reduction. For this question, you would have to go back to the equation, right? And just assign some oxidation numbers. It goes from 0 to -1. So we are gaining electrons, and reduction is gain. So going back, iodine undergoes reduction. that is true. It is not undergoing disproportionation. This term can come up in the diploma, so just know that that is when one of your reactants is undergoing both oxidation and reduction. So just to summarize here, this was 1, 3, 4, and 6. Okay, so moving on from that, we have our next question. It's talking about a battery, and it is first one with question 16, which did test well. It's just understanding your cell. And so during any cell, whether it is voltaic or electrolytic, your anions move towards the anode and your cations move towards the cathode. So because it's asking about the cathode, we're looking at the cations. And then the species at the cathode, cathodes undergo reduction and they gain electrons. So the best answer here is D. Then the next part is asking for the cell potential. Just look at your data booklet. You are getting the cell potential of the first half reaction, then the second. Again, the one that's more positive is your cathode. So the E of the cell is always cathode minus anode. So stick that into your calculator and you'll get 2.05 volts. Oops. Now let's make that bigger again. Oops. All right. So this one, again, it didn't test the best, but that's interesting to me because it's actually not that hard of a question. So this first part says the species that will react spontaneously with Ti positive. Ti positive is here. If it's a spontaneous reaction, we need the OA to be higher. So this first one is number 1. Reducing agent that will not react spontaneously with chlorine gas. So I just added chlorine. If that was on this chart, it would be right under the 2.6 and above the 1.25. So if that was there, what will not react spontaneously with that is going to be number 5. Because, which one are we looking for? You need an OA below it. So I have number 5, and that makes sense because that is an OA below the RA. A reducing agent that is stronger than calcium. So calcium's not on there. If we did place it, it would be between the last 2 reactions. So something that is stronger than calcium would be our options that are listed there. And, reducing agent. Strongest reducing agent is bottom left. So the only option is CS. So that is number 8. So reducing agent, strongest, bottom left, right? Weakest goes up. Then the last one, an oxidizing agent that is stronger than what we see here. Our strongest one is the top one, and that is number 1. And you just want to double check the voltage of that half reaction, but we would be able to confirm that as well. Okay, so this next part we're moving into is organic section. This first one is just being able to look at this structure and describe it. So what we're seeing here, it is aliphatic, but our parent chain has more than 3 carbons. It's not aromatic because you do not see a benzene ring. It's an alkane. It does not contain a double bond, so the only answer here is D that will work. It's an alkane containing a 4-carbon parent chain, which is the chain in here, and only single bonds because we don't see any double lines. Our next one, and again, same kind of idea with this, looking at structural isomers, for some reason always tests pretty poor. So when you're looking at an isomer, you are just looking at the empirical formula and making sure you have the same amount of everything within. So I already went through and counted all my carbons and hydrogens, and the ones that are isomers of the diagram above is C8H16. So you're just looking for the ones that are C8H16. So once you have that, you're just going to write those down. So remember with isomers, that's all we need to do. Get the empirical formula and compare. Question 18, this one is asking about this compound. We know that it's aromatic because there's a benzene ring. And then on the chain, we have a carboxylic acid. So this is D, just knowing our functional groups. Question number 19, we're using this information, and what this information is showing us is that we do have a 4-carbon chain, and we're moving that double bond. So if you move the double bond, you'll see that your not a double bond, we're moving the alcohol group. So your boiling point is getting lower depending on the placement. And so when we're looking at it and it's asking the question about the table above, the alcohols compared, they all have the same molecular or empirical formula. But in terms of boiling point is a physical property, right? Because we're not changing anything. We're not changing the substance. So it's not a chemical property. So that was B. And I think that is also something that throws students off, is knowing the difference between physical and chemical. So if you can't get back to your original form, you are chemical. If you're just melting or things like that, you are physical. Just like color, description of the property, everything like that. Looking at this next one, we're seeing that we're putting these molecules together to create a chain. So when you're looking at ethene, well, first I got ahead of myself. Just describing ethene, anything that has a double or triple bond is now unsaturated, and this always tests well. And then looking at how we make polyethylene is we take ethene as a monomer, and we are, in this case, we're not using an esterification reaction. We are doing polymerization to make that polymer. Okay. Now, again, another isomers question. So if you didn't know isomers going into this diploma, you probably lost a lot of marks. So going through this one, going and just saying what we have, counting your amount of atoms, and then saying which ones are structural isomers. We're just seeing which ones will match. So what do we have exactly the same of? And that is going to be A. The next part, the name for compound 3. So naming this compound, you want to start your numbering from left to right because that will give us the side group first. And if we do that, you have a methyl group on carbon 2 and 3. So that would be 2,3-dimethyl, longest chain is 5, so pentane. And this one tested really well. Okay, this last one on this page is adding bromine to a solution and telling you that the bromine is that color, which is like that dark brown, or sometimes it looks orange, is going to go away. If that happens, that means double bonds are being broken, and that happens in an addition reaction. If the color stays, that means that we're just doing a substitution and there is no double bond present. So with that information, we go back to our diagram and we see where we have a double bond, and we have them all in A. Okay, so the next one, this one is looking at molecule 1, which is this one here, and describing it. There is no benzene ring in molecule 1, so it's aliphatic. And then classifying molecule 2. Molecule 2 is over here, and we do have this link here, and that is an ester link, so this is going to be A. Okay. Now going to the next one, equation 1, we have a double bond present. So we have an alkene, and we are adding a small molecule, and we have one molecule as a product. That tells us it is an addition reaction, and the product is going to be an alkyl halide because you have a halogen now on your chain. Okay, our next one. So kind of switch back to some thermo for a moment, but that's okay. We still have it. In this one, we have just some information. So again, looking at page 4 or 5 of your data booklet, getting some enthalpies. This time we have the enthalpy of the reaction. So when you're looking at delta H of your reaction, oops, nope, doesn't want to write here. Okay, when you're looking at delta H of your whole reaction, and when we say it's products minus reactants, if you have delta H, you're going to be solving for something within the reaction, and we are solving for HCN. So we'll put this on the reaction side. The product side, when we add our two together, is just going to be X, and then we subtract the sum of our reactants. So we'll write that down. Now we just isolate X, and when you do that, you'll see your answer is B. Now with that information, it is saying during the production of that gas, Because it is positive, energy will be absorbed from the surroundings, right? Because it is endothermic. And hydrogen atoms, so going back to this over here, if it's asking about reduced or oxidized, we'll have to take a look. So whether we looked at the methane or the ammonia, hydrogen is +1. On the product side, we have a +1, but we also have a 0. So if we just pick where it's changing, so +1 going to 0, that means you gained an electron. If you're gaining, your reduction. So it's only undergoing reduction. Now, I'm really surprised that this last one doesn't test well, because we do practice this quite a bit, and I'm assuming you would too in your classes, where you're using the Ka formula to isolate hydronium. So you'll get the Ka value from your data booklet, because we do see that this is a weak acid. We are given the concentration of that acid. So get the Ka from your data booklet, use the formula that hopefully you know. We can ignore hydronium in the denominator because we're solving for it. Once you isolate hydronium, and don't forget to square root it once you get that alone, then you plug it in to the negative log formula, and that will give you the pH. So if you did everything correctly, you should get 4.95. So this is just showing you know the Ka formula. They could have asked you for Kb. They could have made the connection that Ka times Kb equals Kw, but they didn't. It was just one pretty simple question. So just making sure that we know that. Okay, number 29, they're looking at the reaction above and asking about oxygen. So if you take a look at oxygen, it is 0 here, and on the reactant product side, it's -2. So if you're going from 0 to -2, you are gaining electrons, and gaining means you are, -2 to 0? Oh, that's what I'm saying. Okay, I was getting confused there. You are gaining electrons, so it is undergoing reduction. And if you're undergoing reduction, you are the oxidizing agent. So that's why it's saying oxidizing first. And then in terms of oxidation number, it is getting smaller because it is getting more negative. Number 30, which of the following would increase the amount of chlorine present? So now we're getting into equilibrium. Catalysts won't do anything except speed up the rate of equilibrium. If you decrease O2 on this side, if you decrease it, you would shift left to replace it. So not that. Decreasing the temperature is on the product side. So if you decrease it, you would shift right to replace it, and that would produce more chlorine. So that one is going to be B. Okay. The next one is using an ice table. So we have the reaction, and then you put 3 moles of the C7H14 into a 1 liter flask. So we have 3 moles per liter of the C7H14. And then initially, because it doesn't tell us, we could assume you have no product, right? So that's our beginning part. Just remember, I has to be concentration. So if there was any number here other than 1, make sure to divide. Your concentration is based on the mole ratio. So reactants are used up, so subtract them. Products are formed, so add them. So if you're confused why the 3 is there, it's because of 3 moles of hydrogen. Then to get equilibrium, add your I and C together. So we'll have 3 minus X. Here we'll just have X, and the last one 3X. Now we did all this work, and then it does tell you at equilibrium, you have 1.2 moles of H2. Again, equilibrium is going to be concentrations. We're lucky with the 1. If it's not 1, make sure you're dividing. But what we can do is set our 3x equal to 1.20 and solve for x. And you'll see that x will equal 0.4. Now that we know x, you can go ahead and plug it in to figure out the concentration of C7H14 and the concentration of C7H8. Once you have that, then you can go to your Kc formula, which is going to be the concentration of the products. Don't forget that you need to add the exponent if you have a coefficient in front, and divide by the reactants. So once you solve for this part, you'll see that it's 2.6. You plug that into your calculator, and you'll see your answer here is B. Moving on to the next one, we have the equilibrium equation, and it's saying that if it is cooled, the equilibrium will shift. So if it's cooled, you're decreasing temperature, you're going to shift right to replace it. So you'll end up producing more of the product. So we can take that out. And then Kc is the only thing that can, temperature is the only thing that can affect Kc. So if there was any other shift, Kc would stay the same. But because we are making more product, if you have more product, Kc goes higher. So Kc is going to increase. Okay, this one, question number 33, we want to be able to tell what's happening within the system. So what we can see is that reactant being used up. So we know that NOCl is what we started with as reactant, and products are produced. So we can see where our products are going to be. The other part with this is you do want a balanced chemical equation. So just by plugging it in, it wasn't balanced. So you do have to rule out A and B. And then it's just showing, how to set up the Kc formula, taking those coefficients and making them exponents. So here the answer is C, and this one tested well. So it looks like a lot of students can do that. Oh, maybe I got that one. Nope, that was right. Sorry, I was looking at the wrong question on my little cheat sheet in front of me just to make sure I have everything correct. Okay, so then this next one is showing with that equation, going back to this for a second, that we understand equilibrium. So if we are in equilibrium, right, because it's saying at the 10-minute mark, and if you go back to the graph at the 10-minute mark, equilibrium has been established. We know that because of these horizontal lines. So if equilibrium's established, then we want to make sure these statements show that we're in equilibrium. So if you are increasing or decreasing, you're not in equilibrium. So we're looking for those words like constant, stay the same. So we're taking out number 1. We know it's going to be number 2, not number 3, but number 4. The pressure, well, we're not going to change it. Pressure will remain constant because you're in equilibrium. And then lastly, knowing the equilibrium definition, the rate of the forward reaction is the same as the rate of the reverse. Can't be number 8 because of that greater term. It needs to be the same. Okay, so this next one, we have citric acid, that's a solid, was added to a flask of water, then stopped. How can we tell equilibrium was established? If you are in equilibrium, that means there's some sort of change. So this one is kind of like that physical equilibrium. So at the same rate, the solid is breaking up, the ions in the liquid are going to make the solid. So we wouldn't have it completely dissolved or it wouldn't be in equilibrium. The forward and reverse reactions have not stopped. They are the same. The pressure of the system is constant. We wouldn't really be able to see that, but what we would be able to see is A. The mass of the solid is going to remain the same, even though it is changing to ions, and the ions are making that solid as well. So for that one, it's thinking about that saturated solution. Okay, number 35, we are asked to look at the reaction for hydrogen sulfide and aqueous sodium hypochlorite. So looking at the Bronston-Lowry reaction for this, we're taking a look, and you can take out the first two because we need to see those ions. And then when it says the reaction favors we would just look at your data booklet and look at placement. And when you look at placement, the acid is higher up on the table and then the base. So if that's the case, products are favored. If the base is higher than the acid, then it would be reactants favored. Okay, the next one, looking at the equation above, the Bronston-Lowry base. So looking at the base, we have the hydrogen being donated, and on this side, the hydrogen being donated. So the base is going to be the F negative, and then it's conjugate acid. So to be a conjugate acid, it's a difference of 1 hydrogen. So the answer is going to be C. This next one, absorbic acid. We have this as absorbic acid. And because you can donate more than 1 hydrogen, it's polyprotic. And then asking about its conjugate base. So its conjugate base is this one over here. And because you have 1 hydrogen and a negative, that means you're amphiprotic. You can act as an acid with that hydrogen and as a base with that negative. So this is C. This next one, always look at how this would be ordered in your data booklet. So if this was in your data booklet, these two reactions would be flipped. And so then going through that, unless you just can tell, but I like the order of the data booklet, the ammonium ion, because it is stronger than the, okay, I guess I just answered that. It is stronger, not weaker, because it would be higher up on the table than the base. And then we know that because it has a larger Ka value. Okay, so if it's not in order, you might want to write it in order first. Now this one, again, this did not test well at all. Going through this one, it's asking from lowest pH, so you want the strongest acid, to highest pH, so weakest acid. So just remembering the pH scale 0 to 14, the closer you are to 0, the stronger you are. All right, so the one with the lowest pH, if you look at your data booklet and you're looking for your lowest pH, you are looking for your strongest acid. So in terms of placement, your strongest acid is this one here. And then once you start reacting, we're going to lose a hydrogen. So then the next strongest would be number 1, because that's showing you've lost 1 hydrogen. Now from here, when we're moving on, we are going to see that you have that kind of buffered solution for a second where this hydrogen is going away, and in equal concentrations, if that hydrogen goes away, we also have this, so that would be number 4. And then lastly, if we only have this last one with 2 negative left over, then that is going to be the weakest acid with the highest pH. Number 39, same with the Bronson-Lowry conjugate acid. If this is our base, you're a difference of 1 hydrogen. So looking at this formula, just add on a hydrogen, which would come with a positive charge, and that is A. This next one, if you're titrating your acid with sodium hydroxide, that means you are adding sodium hydroxide to the Erlenmeyer flask. So you're starting with the acid. So we're looking for one of the graphs to start with the acid. So it's C or D. And then if it's asking which one we have, we want to see that this one is showing monoproduct. And because here you have 2 equivalence points, that is polyproduct. So looking at the fact that you have 2 hydrogens you can donate, this is going to be D. 41, which of the solutions has the lowest pH? Lowest pH, again, if you look at your scale, means you're the strongest acid. So here you're just looking at page 8-9 of your data booklet, and the acid that you see to be highest on that list is D. 60 here, we are mixing these together. What can act as a buffer? So a buffer, again, difference of 1 hydrogen, but they have to also be weak. So the first one doesn't work because that's strong acid, strong base. The second one doesn't work because I believe we still are too strong. So this last one, once we split into ions, we'll see we're a difference of 1 hydrogen and we're weak. So the answer here is D. Okay, this one, number 43. Again, this one did not test the best, but going through, we have our pH curve, and then it's asking what the tablet could be classified as. So if the tablet was in the unknown acid, so here is what we're looking at, the starting point, we can see our, sorry, I did circle it, it's just not cooperating anymore. The starting point is between 2 and 4, so that would be a weak acid. And then we can see from the graph that there's only 1 equivalence point, so it would be a monoproduct weak acid. So that answer was B. Maybe my pen died. In number 44, oh, this whole thing died. Frick's sakes.